in Greek civilization around 400-ish BC and maybe to 200-ish BC, the development by people like Plato and then by people like Euclid. And in a sense, what they thought about was, how do you take this very practical mathematics that we do, and how do you make it something, how do you really talk about the abstraction that's involved in that mathematics? So it's one thing to say there are these specific numbers and you do this and you do that, but there's this kind of idea of numbers abstractly or triangles abstractly, not this particular triangle that's used to, the layout of this field and so on. And one of the things that came about was, which was particularly prominent in Euclid, Euclid was a mathematician who worked in Alexandria at the Library of Alexandria, kind of an early version of a university in Egypt, in maybe 150 BC-ish time frame. Essentially nothing is known about his life. Only his works survived. His works were the second most published book in history for a long time, after only the Christian Bible. So the thing that, what was in Euclid's books? Well, what it is a way of talking about geometry that is, in a sense, abstracted. It says, for example, consider the concept of a point, consider the concept of a line, consider lines that are parallel. What implication does it have if you say that lines are parallel and then this is true and then that's true? How do you infer kind of logically some result? And in Euclid, you go through, he has kind of about 10 axioms at the beginning of things that he claims he's going to use as part of his system of logical deduction. And there's the very first common notion of Euclid is a point is something which has no part. A point is something indivisible. There is a notion of a geometrical point. There's a way of just having a point in space and having it be the case that that is just one place and that it has nothing inside it. And then the second statement is a line is something which goes between 2 points. And then it builds up from there, and it builds up in Euclid's actual works. It's got about 460 results that come out of those axioms at the beginning. And the final and most difficult to derive result is the result that there are 5 Platonic solids, that there are only 5 figures that where all the faces and corners are the same, just the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. The fact that in 3-dimensional space, those are the only regular solids. That is the sort of the pinnacle of achievement in Euclid's books. And he derives that on the basis of these, purely in a sense logically, on the basis of these fundamental kind of propositions that he asserts about space. I think what he thought was that those were mere crispenings, condensations of things that everybody sort of knew was true, like 2 parallel lines never cross. That's that's the 5th postulate of Euclid, is that if you have parallel lines, they just stay parallel, they never can cross over. And he just took that as being a kind of a precise statement of something that was obviously true about the world. That was something that was just a fact about geometry. I don't think he really understood the extent to which that fact might depend on the physics of the world, to what extent that was a feature of human thinking about the world. He didn't really tease apart those kinds of things. But to him, what he was doing was he was writing down a kind of an axiomatic system that would describe in precise terms the world as he thought the world was. And then on the basis of that axiomatic system, he was able to make purely logical deductions. In other words, there was sort of a distinction made between things that were merely a matter of opinion. Oh, this might follow from that, and somebody might disagree about this and so on, versus things which were just a matter of, in a sense, precise deduction, that you didn't have to say, you might say, all sheep are white or something. Well, actually, there's a black sheep somewhere, and it might be wrong. But once you have these logical, in a sense, these formal axioms of Euclid, once you say those are true, there's a whole bunch of other stuff you can deduce. And the deduction of that other stuff doesn't have the possibility of saying, oh, whoops, it turned out there was a black sheep. It's something which can be, as a pure abstract matter, as a feature of sort of abstract necessity, those things will follow, given the assumptions that were put in at the beginning, the axioms that were put in at the beginning. Euclid, I think, believed that those axioms were kind of a matter of a description of the world that was sort of an obvious feature of the world. Now, a lot happened after that time, after Euclid kind of defined this kind of axiomatic, abstract way to deduce things about mathematics. That was something that was a kind of a highlight of kind of abstract thinking for a couple of thousand years. And it was used as an example endlessly by philosophers and so on to distinguish things which are just kind of happen to be true about the world, that it sort of might happen to be true about the world that we have 5 fingers. It was because the critters who had six-fold symmetry or something back in the Precambrian period happened to die out because of this thing, some accident. It's just a contingent, a thing that happens to be true about the world. Or so we might think. We don't know for sure, something like that. It's very hard to know for sure what is just happens to be that way versus what has to be that way. I mean, a notable feature in modern times is, it always used to be the case when I was a kid, that a classic example of a contingent fact about the world is that there are 9 planets in our solar system. There were 9 then because Pluto still counted as a planet. But the fact that our solar system happens to have 8 planets, 9 planets, whatever, was viewed as being something which was just, it happens to be that way in the world as the world happens to be, rather than that is something that we could derive as a matter of abstract necessity. Now that we know, I don't know what it is, 5,000 planets around around many different stars, we know that our solar system is the structure of our solar system is something which, well, it's actually a little bit unusual, but it's fundamentally a derivable thing. Given that you have a star of the size of the sun, et cetera, et cetera, et cetera, you can more or less say they're going to be about 9 planets. Now, there are details about, well, maybe there were planets that collided with each other. Maybe there's weird things about Jupiter and Saturn being comparable in size, and that leading to inner planets that didn't collide with each other, and et cetera, et cetera, et cetera. Lots of details. But fundamentally, it no longer looks like a random fact about the world. It looks like something which is conceivably derivable. So exactly where those boundaries are isn't completely clear. But at least at the time of Euclid, I think he thought of himself as taking what was in a sense obvious from human senses and crisping it up to make something which could have deductions done from it, which would be then true about the world, because the underlying stuff was kind of obviously true about the world. Well, what developed in mathematics in the following couple of thousand years, there was a lot of practical development of, well, mathematical notation was a big thing about 400 years ago that sort of launched what became algebra, later calculus and so on. There got to be much more sophistication in the kinds of ways that one did mathematics. When Euclid was doing it, he was using words only, and people then added pictures, geometrical diagrams, and later on people filled in proofs that were sort of standardized forms of the proofs for Euclid, although Euclid himself just said, here's a statement, here's another statement, here's another statement, rather than himself giving the proofs. So then the thing that happened in the 1800s was that a lot of things that people sort of thought were self-evidently true people started questioning them, like, do parallel lines never cross? There was a big thing, a chap called Lobachevsky was the big one for pointing this out, that, well, actually, if you have a curved surface, like on the surface of the Earth, you draw 2 parallel lines, they actually can cross over, depends on how you draw them, so to speak. Sort of a famous example would be two lines that you might draw at 90 degrees to each other, one going around the equator, one going around meridian around the Earth. Those lines will certainly cross over, even though if you drew them in the plane, for example, two lines which are at 90 degrees, they'll just go out forever. So in a curved space, that isn't true anymore, that parallel lines will never cross. And the real question was to, first of all, have the idea that mathematically, abstractly, we can imagine a curved space. It then took until 1915 or so when Einstein sort of pointed out, actual physical space is curved. And so parallel lines, parallel beams of light, for example, which light follows kind of the shortest paths, those parallel lines can cross. And for example, if you have two beams of light going around on opposite sides of a star or a black hole or whatever, those beams of light can be, it's gravitational lensing, it's called, those beams of light will be gradually pulled together and it will eventually cross. And so it is neither true in principle that parallel lines can never cross. You can imagine a curved version of space in which they cross. And moreover, it turns out that our actual physical space of the universe in which we live has the property that it can have curved parts where, in a sense, parallel lines drawn in physical form can cross over. And so what happened in the early 1800s, 1830s, and so on, there were a series of things like that. There was Lobachevsky and parallel lines and curved space. There was Galois theory, the theory of groups, where one had things where one had been thinking about things like numbers, x and y, and you would say x times y is equal to y times x. Well, actually, if x and y represent things that are sort of generalizations of numbers, it might not be true that x times y is equal to y times x. That came up in group theory. It came up in the theory of quaternions. That was, again, a place where one sort of generalizing the notion of arithmetic. Came up in Boolean algebra from George Boole in 1830s or so, where there was kind of a formulation of logic where it was ands and ors are like roughly like pluses and timeses, but they're not quite like pluses and timeses. They're kind of a generalization of that. And so what came into existence was this idea that you could sort of just write down an arbitrary axiom system for the world, and then you could write down an arbitrary axiom system and then you would deduce things on the basis of that axiom system. And that, in a sense, through the period of the 1800s, that became viewed as kind of the what was mathematics. Mathematics was, in the time of Euclid, mathematics had been, it's really about the way the world is and our perceptions of the world and kind of a crispening up of that and the ability to make sort of deductions on the basis of that. But by the 1800s, it was more just put down whatever axioms you want, and then we can deduce things from it. In a sense, the content of mathematics started to be about this process of deducing things from axioms. Where the axioms came from, that was kind of arbitrary, but the deduction from the axioms was the stuff of mathematics. So it didn't matter. So the question of, was what you were getting out fundamentally true? Well, not really. It just was a matter that the deduction from the axioms could be fundamentally true, but the axioms themselves, it might be the case that you had a positively curved space and negatively curved space. You might have xy equals minus yx. You might have this, you might have that. It was sort of arbitrary what those axioms were, but then you could build this whole tower on top of those. And this kind of came to a head in the late 1800s to the beginning of the 1900s, when people started imagining that really mathematics should be built. It was sort of this arbitrary structure built on top of whatever axioms you chose. And famously, a chap called David Hilbert, who was a famous mathematician around the beginning of the 1900s, was like, actually, mathematics could be about tables and chairs and beer bottles as much as it could be about lines and points and planes. And that the kind of the statements of mathematics were purely abstract structural statements, completely independent of the stuff that they were talking about, anything that we would consider to be a thing that we can have sensory data about, because we can have the idea that we think we know what space is. We move around in it. There's certain distances in it. We have as humans, we have a definite kind of sensory opinion of space. But the idea of Hilbert was mathematics is really not about that. Mathematics is about this pure abstract structure. And so that meant that mathematics was, in a sense, something that was mechanizable. Once you had it as a pure abstract structure like that, you could just say, I'm going to take what Euclid did and I'm going to make it something where I can essentially have a machine that will go through and deduce all the true statements based on the axioms that, for example, Euclid had written down. Now, at the time that Hilbert was doing this, at 1900 or so, computers didn't exist. There were mechanical calculators that did arithmetic and so on, but the idea of electronic computers and so on was still a solid 40-something years in the future. And the idea of computation as an abstract thing, just as in the early days of the creation of mathematics, people had abstracted the idea of numbers away from numbers of goats and so on. People by the 1930s were abstracting computation away from the specifics of which computation are you doing, the notion of computation in the abstract, so to speak. And that was what Alan Turing and people like that did in developing kind of this abstract notion of computation. So the question that I should say, by the way, that this idea of mechanization that Hilbert had, he particularly was interested in doing it for Euclid. The interesting thing is we finally more or less done that in Wolfram Language recently. We've been building kind of the ability to reason about geometry and to represent kind of geometrical facts as symbolic statements that can be mechanically handled. That's something finally in 2021, 2022 is something that we are achieving, that the computationalization of what Euclid did a couple of thousand years ago. But anyway, when Hilbert had this idea of let's just take the axioms of mathematics and mechanically deduce everything that's true from them, the big kind of the very bad thing from that point of view that happened was in 1931, Kurt Gödel proved this thing called Gödel's theorem, which said actually there will be things that you can write down that seem like they're statements about arithmetic, things like this particular kind of equation, x cubed plus y cubed equals z to the fourth minus 7 or something. You have an equation like that, and the question is, can you prove that that equation doesn't have any solutions, let's say, for integer values of x, y, and z, for whole numbers x, y, and z? And that what he showed is that there are statements that are as sort of arithmetic-like as that, but which the axioms that people had written down, the so-called Peano axioms for arithmetic, simply couldn't reach those statements. It couldn't tell you whether those statements were true or not. The sort of the axiomatic system, just there were, in a sense, if you were going to make a proof of that, the proof might be infinitely long. It might not be possible to have any finite proof of that statement. And so that was something Gödel established in 1931, and that very quickly made people say, oh, this pure mechanization of mathematics is not going to work. Now, the effort to have started that mechanization was what led to the idea of computation and led to everything we have today in software and in the whole sort of computational paradigm that we have today came out of essentially a failed attempt to understand kind of the foundations of mathematics and what mathematics really was. But if you ask a typical working mathematician today, what is mathematics? What is it built on? What kind of a thing is it? Many would probably still say, well, ultimately you can kind of dig down underneath all the mathematics we're doing, and it's certain axioms. And the usual ones that they'll quote are the Zermelo-Fraenkel ZFC axioms of set theory, which are extremely obscure and abstruse things that are very much not very close to any kind of human kind of intuition about what's going on, because they talk about sets. A set is just a collection of things. A set is sort of like numbers being an abstraction of numbers of goats, numbers of sheep. A set is an abstraction of just a collection of things. They could be sheep, they could be goats, they could be numbers, they could be lots of other things. But then the kind of thing that one starts to talk about is, well, what happens if you have an infinite set? Like, for example, the set of all integers or the set of all real numbers. What can you do with those infinite sets? What's true about what happens when you combine two infinite sets? Can you always pick things out of both sets, and how does that all work? Those become the axioms of set theory, and they are not very human intuitionally connected. They're things that are quite abstruse pieces of mathematics. And in principle, the edifice of mathematics that exists today, about 3 or 4 million theorems people write down in the literature of mathematics, have been published over the centuries, most of them very recently, because things are, there are more and more there are many more mathematicians alive today than have ever lived in the past. So it's an expanding kind of area. But the question then is, what really is it? What are the things that one is building? Is it really built from the ZFC axioms of set theory? Is that really what mathematicians think they're doing? It's not what mathematicians mostly think they're doing. But there is always this kind of thing where, in principle, we could drill down and we could find what we are rooted with. Our foundations are on top of set theory. So people might say it isn't probably true, because in actuality, what mathematicians will do is they try and establish things that they think are true in some sense, but they will do it using things that they kind of assume are true. And just like Euclid assumed that parallel lines could never cross, there are things that mathematicians implicitly or explicitly assume are true on the basis of kind of their intuition and kind of the collective beliefs of mathematicians over the ages. And those are the things from which mathematicians try to develop proofs of results today, which are perhaps, and the results that they might prove maybe things very far away from things about which we have intuition. But the proofs end up being things that go back to things that seem like they're true. And that's kind of the practical definition of proofs in mathematics, is you're making some kind of narrative explanation of why something is true, using these often fairly precise methods to say, okay, this is true based on what we think is true down here. Now, people sometimes say, but in principle, we can drill all the way down and get to the underlying axioms of set theory. But in practice, people don't do that. There's been an effort to kind of formalize mathematics, to use particularly proof assistant programs, where you as a mathematician are saying, I'm going to try and start from these foundations, and I'm going to fill in puzzle pieces to get to some result that I want. But it's a very arduous, time-consuming thing to do that. And it's something where it is the big surprise. One of the big surprises is you can actually change the foundations a lot and not change many of the results which are deduced. So, for example, some fact, some theorem, the Pythagorean theorem, the fact that the sum of the x squared plus y squared equals z squared for the edges of a right-angled triangle, that's something where you could get incredibly pedantic and persnickety and say, well, what exactly do you mean by the length? That's defined by a real number with an infinite number of digits, and you've got this kind of thing going on with that. And what do you mean by equality? What happens if the infiniteth digit is different, et cetera, et cetera, et cetera? You could get very persnickety about it. But it turns out the theorem is true for many different versions of that persnicketyness. So in a sense, it's a more robust general statement about something related to mathematics than it is about these axiom systems. And I've sort of realized recently, I've kind of changed my mind about how this works, because I've been working on metamathematics and the question of sort of what is the structure of this thing that we're creating from axioms. We can make proofs of theorems. Any given theorem might have many different proofs. What's the role of those different proofs? How do you get from one proof to another proof? What kind of a thing is that, and so on. How do you think about those kinds of things, and what in the end is this thing that mathematicians do that they call mathematics, that is somehow you can, how does it relate to these sort of axiom systems you can write down? And what I've sort of realized is that the mathematics that people do is very humanized mathematics. They're thinking about concepts that humans care about and can think about. At some level, you can drill down sort of below that level to things where you're looking at the individual axioms and everything that's happening there, and you get this kind of machine code version that's very incomprehensible to humans. And you can actually drill even further down than that, I've realized, to something even lower level. But it's not, but the thing that people, humans, view as being the stuff of mathematics is something at a much higher level. It's kind of like when you do, when you study physics, if you have a flow of a fluid like water or something, that's at a sort of human scale, and you can see various features, and you might see a vortex, things like this. But down underneath, there are a bunch of molecules bouncing around. And so it is, I think, with mathematics, that the mathematics that mathematicians deal with is more at the level of kind of things like vortices. It's more at this kind of large human scale, whereas sort of underneath that are sort of the micro details, the machine code. You can go to the axioms, you can go even below the axioms. I think the thing that is kind of the ultimate object sort of below the axioms is the thing I call the Rulliad. And the Rulliad is the following thing. So imagine all possible rules for doing computations, all possible rules by which you might take some array of black and white squares. You might have some rule that says what happens to each black and white square. You might have some network which is defined by certain relations. You might say what happens when these relations are combined. These are all rules for doing different kinds of things. Let's just imagine that you could just get all of the possible rules for things, all possible definite rules for things, all possible things about which you could have definite rules. And let's say you just run those rules and you run them for an infinite number of steps. What you have there is this thing I call the Rulliad, which is the sort of entangled limit of running all possible computations for an infinite number of steps. So you might say, well, how can that possibly be anything other than just a complete mess? But the thing is, it has a very definite structure, because you can have two computations, they start in two different places, they end up producing an equivalent result that produces some kind of structure in this Rulliad. You can keep going, and you've got different kinds of structure produced when things branch, et cetera, et cetera, et cetera. So in the end, this Rulliad structure, which is the entangled limit of all possible computations. So it's not like I'm picking these computations and not those ones. It's like you take all possible computations, and there might be different ways to represent those computations. You take all possible ones, that ends up being this object that I call the Rulliad. And one feature of the Rulliad is there's only one of it, and you are basically, it is a necessary object, as necessary as, given the definition of 1 + 1, that it's equal to 2. It is similarly necessary. There's nothing about it that is, oh, it happens to be that way. It doesn't happen anything. It is necessarily has the structure it has. And so one of the things that is sort of a big realization of the last year or so for me is that sort of everything we experience in both physics and mathematics is kind of a sampling of the Rulliad. That the physical world is actually what's ultimately real is the Rulliad, and we are basically, as observers of small pieces of the Rulliad, we get to observe those small pieces, and we kind of name the aspects of the Rulliad, things like space and time and electrons and things like this. But those are our particular way of sampling the Rulliad, gives us these particular features of our world, the one that we perceive physically. And an important aspect of this is the notion of time, which is kind of this progression of these computations in the Rulliad, or the notion of space, this idea that there's a certain amount of uniformity in the Rulliad, so you can essentially take you and your sort of sensing of the Rulliad and move it to somewhere else. And that's possible to do without you getting shredded to pieces, that motion is possible, that even though as we move around, we might be made from different kind of atoms of space, that still there is an identity to us that we can carry around as we move around. And that's kind of the notion that there is a thing like space. And that's another feature of the Rulliad, is that there can be a thing like space. There can be a thing like time. There can be a thing like space. The way we as sort of observers of the Rulliad sample the Rulliad with our particular senses and our particular kind of capabilities of our brains and so on, we sample it in such a way that this is what we perceive about the world, that it has space and time and the other features of physics as we perceive them. Well, the thing that is part of the sort of fairly recent realization is that mathematics is also just the Rulliad. And our experience of mathematics is based on sampling the Rulliad in certain ways. And you can certainly sample it to correspond to what will be the consequence of this particular axiom system. But the Rulliad has sort of all possible axiom systems in it. So in a sense, your decision to sample this particular axiom system is a decision on the part of the observer. And what's a little bit confusing is that there's actually a level below the level of axiom systems. The raw computation on which the axiom systems are based is this sort of raw Rulliad level, the level of pure raw computation. And so you might ask, well, what are the things that that raw computation is dealing with? In the case of physics, we think that raw computation, we can identify the things it's dealing with, and they're the atoms of space, the elements of what make up the structure of space and the structure of everything in our universe. In mathematics, what is below axioms? What do you make those axioms out of? When you have some variable in the axiom system, what is that ultimately computationally made out of? What does it sort of compile down to? And there's this kind of notion of the thing we're calling EMES, E-M-E-S, that are the fundamental elements, the lowest level elements, the kind of atoms of existence, the things that are the lowest elements from which you can make mathematics, you can make physics, where the EMES are identified by the atoms of space and so on. One of the consequences of this view is that, in some sense, physics and mathematics are built on the same thing. They're both built on the Rulliad, and they are, in a sense, they are the same thing in some sense. They are simply being observed in different ways. You get physics, you get mathematics. Another consequence that has is, remember I was talking about Euclid having this view that mathematics is something which is a crispening up of common human experience. Well, now we've got a picture where, in a sense, mathematics is an extraction from the Rulliad made by human experience, just as physics is an extraction from the Rulliad made by human experience. And the question is, and that then gives one the idea that mathematics has a reality to it, just like physics has a reality to it, that is something extracted by our human experience. And so, for example, Kurt Gödel, when he proved Gödel's theorem in 1931, one of the things he was trying to do was to show that axiom systems weren't the full story, that in fact, one could have a direct notion of truth in mathematics, and that axiom systems were just kind of a distraction. I have long assumed that axiom systems were not a distraction and were the real thing that was the underlying structure of mathematics. But I've recently kind of come to the conclusion that's just not right, and that Gödel was more correct in believing that there's sort of a reality underneath mathematics that is something very similar to the reality of physics. And in a sense, as soon as we say that the physical universe exists, which is kind of a very basic statement to make about the world, the universe exists, it's not just that we have a pure consciousness, we're thinking about things and there really isn't an outside universe. As soon as we have the idea that it's worth saying the universe exists, then it will be a necessary thing to say that similarly mathematics exists. There's kind of an idea often attributed to Plato, kind of Platonic notion of ideal forms as a kind of a thing in the world, distinct from kind of the outside world or our internal experiences and so on, this kind of world of ideal forms that were somehow some kind of abstraction of those things, well, but that were somehow real in some sense. Well, this whole argument about the Rulliad and physics and mathematics being the same and so on is very much in that direction of saying that there is a real thing underneath mathematics and so on. So this is kind of a what is the thing of mathematics. I find it amusing that there's people sometimes for some reason, there's an intersection between interest in kind of blockchain and kind of the notion of sort of blockchain. It's kind of like computation is going to run the world, which is undoubtedly the case, and that in a sense, computation, you might think, has its foundations in mathematics, and so that these kinds of axiom system in mathematics and so on will ultimately flow through to being the determining kinds of things that will sort of specify how the blockchain that runs the world kind of thing works. I don't think that's quite right, because I think that the real story is that computation is a more general kind of thing than mathematics, and these axiom systems from mathematics were chosen with some arbitrariness. And one might even say that one of the sort of concepts of the whole blockchain world is how much it's possible to sort of factor out the notion of governance and governments and countries and things like that from the whole picture of the way the world is run, that it's sort of code is running the world, so to speak, as opposed to something that is some kind of human enforced rule of law and so on. I'm not saying that's a good idea, but that's kind of the concept of sort of the philosophical, the political philosophy of blockchain is for many people is something of that kind. And so it then becomes something of an irony if you say, well, you know, we really believe below all this blockchain layer of computation and so on and so on and so on, it's all eventually going to be based on mathematics. Well, and then the mathematics is all, well, it's all based on the ZFC axioms of set theory, let's say. Well, that's not really, that's really kind of it's not the right thing. It's sort of interesting though, if one takes the point of view that one's factoring out kind of the governance of sort of the world into these sort of lumps of computation, but you say, but they are going to be rooted in something we know is true, the ZFC axioms of set theory. Well, that's not really right, because those are a human construct, and they're actually a human construct that doesn't even capture what we want to do in mathematics. There are things that are undoubtedly assumed to be true by mathematicians, which are not captured by the axioms of ZFC set theory. And so it's kind of the concept that there's sort of a below everything, all that the mathematics is solid, even if we don't know what the constitution of the world should be for the AIs and so on, even if we might argue about that, well, at least there's a layer of things which is mathematics, which is undeniable. Well, that's just not true. You can absolutely write down an axiom system and try and work out its consequences, at least until you get bitten by Gödel's theorem. But the idea that there is a sort of as to quote something which is sort of referring to sort of truths to be self-evident, so to speak. That is this idea of sort of the necessary truth. And when one tries to like in a constitution or something, one says hold these truths to be self-evident, which is, by the way, an interesting construction, because to hold these truths to be self-evident is different from saying the truths are necessary truths. And so in a sense, that's like setting up an axiomatic structure like Euclid. We hold these truths to be self-evident, then we're going to build this whole structure on the basis of that. Is kind of a Euclidean kind of construction at that level, and an interesting one, and a good way to formulate that way of thinking about things. But I think that the thing to realize is that when anything you might say there is there is no ultimate, this is how it is, and there's nothing else, no other way it could be. One of the features of this idea of the Ruliad is that all possible rules are there, all possible crazy things that can happen in the universe are there. But the fascinating thing, which is a matter of essentially mathematical analysis to show that it's the case, that for an observer like us, we necessarily perceive things like space and time and gravity and so on. And that's a consequence of us, observers like us, with our kinds of sensory capabilities and so on, will necessarily perceive in this giant mass of all possible rules that is the Ruliad, we will perceive these particular features of slices of the Ruliad. And our friendly aliens, for example, might perceive something utterly and incoherently different. And that's an issue for us in terms of like, hello aliens. It's like they may be separated both in physical space and what I call rulal space, in this kind of, how do they slice the Rulliad? Is their slice something where they say, I don't care about space and time. I care about these other concepts that reflect some precise detail of how the atoms of space interact in this way and that way. And we're like, we don't care about that. That's something way down, 10 to the minus 100 meters in size, trillions and trillions and trillions of times smaller than anything we can sense. We don't care about that. We care about whether you can, walk across the room. And they say, what do you mean? What's the structure that's walking across the room? We don't see a structure there. All we see is a bunch of configurations of atoms of space that have this or that feature. And we really care about those things. We don't care about the fact that the atoms of space are arranged to make the matter, to make the physical atoms and the matter and so on that makes you. That seems like an irrelevant thing to us. What we care about is these sort of micro details of the motion of atoms of space, for example. And so the idea of this kind of notion of the Rulliad is that there is an abstract necessity, but it's an abstract necessity that contains everything. But there is a contingent fact about that is the way in which we sample it. We as humans who've evolved in the way we have and have learnt things the way we've learnt things, we sample it in this way. And so that's what we perceive about the Rulliad. Now, of course, you can say, well, what's going to happen in the future? Are we going to sample things differently? And the answer is yes. As our technology evolves, as our ways of thinking about things evolve, we will gradually move in rulal space. Just like we're sending out spacecraft in physical space, we are, in a sense, by the developments we make in science and in intellectual issues, we're gradually moving in rulal space. And we're able to see sort of more of this Rulliad that is the underlying thing that represents everything. The Rulliad is very big. It's maybe, I don't know, I had some estimates of 10 to the 10 to the 350. So let's see, it's a 1 with 350 zeros after it, and then it's that number of zeros after a 1, roughly. I mean, that estimate is probably not exactly right, but that's the kind of, that gives you a sense of everything that there is, at least to this moment in the existence of our universe, so to speak. And so, we represent, just like we might think we're kind of small because we represent only this, these critters that are on planet number 3 of this solar system, on the somewhat outer reaches of this rather typical spiral galaxy, in this rather typical cluster of galaxies, in this, in the universe, so to speak, that we are at that level of smallness relative to the universe, and at that level of kind of arbitrariness with respect to the universe, it gets, there's much further down. By the time you're looking at this whole Rulliad of possible rules and so on, it is much, much bigger than the physical universe. The physical universe is but one tiny slice of that whole Rulliad of possibilities. And that's kind of it's something that's sort of interesting to think about, but in a sense, the slice we're on is the slice that is a representation of who we are, so to speak. And it's not the case that in some sense, that slice is arbitrary, but in some sense, it's maybe less arbitrary than saying we happen to be on this particular planet in this particular solar system, this particular galaxy, and so on. It might be a little less arbitrary than that, given the way we are, so to speak. There's kind of that determines which slice of the Rulliad we're on. Now, you could also argue that we are the way we are because, well, gosh, our night sky isn't bright at night. We're not near the center of a galaxy with tons of stars in the sky. We're not this and that and the other. We're not, you could make a lot of arguments about that. Well, anyway, that was a long description of a little bit about sort of the way of thinking about mathematics that I at least have evolved in recent times. And I'm just in the process of writing this giant thing about this. There's a question here from WW asking, in what ways am I better than an AI? Well, we have to kind of define what we mean by better. I think I would say the following thing. I've been kind of wondering, I store a lot of stuff that I do. So I store every keystroke I type, I do these live streams. There's a lot of me out there that is recorded. And the question is, could you take all that stuff recorded about me and make a bot that is me or a better me from all that information? In other words, the information that I'm recording is not a small fraction of all my sensory experiences at this point. It's a decently large fraction of them. And given that, could one use that to essentially build a better me that is a pure AI? And the answer is, I suspect, we're not quite there yet, but for some purposes, yes. On the other hand, there is a notion, and this is generally true about AI. AI, in some sense, is an automation process. It's a take what we knew we wanted to do and figure out how to do it automatically. The issue is, what do we want to do? And that's something where I don't think there's, just like we're talking about mathematics and its foundations, and there's no necessary foundation of mathematics, there's no necessary constitution for the way things should be in the world, there's no necessary set of goals for everybody should want to do this. It's something where, in a sense, that's the main thing that we humans sort of have over the concept of the AIs, is the what do we want to do type question. And that's something which is sort of a feature of our history and lots of other aspects. But that's something that sort of the initiative, so to speak, is something that is an arbitrary thing chosen by us. Now, we could certainly make an AI that will imitate the creation of that initiative. And in a sense, from the outside, you might be able to see no difference between those things. But from the inside, it feels like we are trying to get things. We have certain goals that we've developed. And this is a different thing from what we would be seeing in an AI. We could have, the AI will have no, unless we give it some goal as a principle for making goals, it does not have an intrinsic way to make goals. So I think that's one thing. I think as a practical matter today, I'm perhaps either proud or sorry to say that I think I do a lot of things that are not readily doable by an AI. I think, an interesting question is I write lots of Wolfram Language code, write lots of computational language, and is that something an AI could do? Well, the answer is no, not really, because it is an expression of things coming out of my mind right now. It is something where I'm trying to go, and the goal of language design is to go as directly as possible from the way I think about things to a representation in computational language. And I just don't think that that's something which almost by definition is not AI-able in the current state of in that sense. Let's see, there's a question here about saying JavaScript will run out of milliseconds. This is from Aaron. In 270,000 years. I didn't know that specifically. It doesn't surprise me. Have I ever written code that created a date object past that time? How far in the future could Wolfram Language represent? Don't know, actually. I think our date objects can have arbitrary length numbers in them. So in a sense, you can probably represent, I'm sure you can represent much further in the future than the universe has existed so far in the past, which is, 14 point something billion years. I'm sure you can represent hundreds of billions of years into the future and beyond that. I think that there's a question of what can you say about times like that. One question is about, for example, astronomical computations. I know that our ephemerides, those are the things that let you compute, positions of planets and so on. We currently have ephemerides that go for a couple of hundred years. I think we're about to extend them to ones that go for a few thousand years. But there's a lot of data to specify the precise positions of planets over that period of time. And if you get beyond a few thousand years, it's very hard to have accurate data because it will matter, what random perturbation from this place or what random interstellar asteroid comes through the solar system and perturbs this thing. These are things that we don't know and we can't sort of formally compute, so to speak. So those are um, but now in terms of how far, I have various kinds of systems that send mail and do things at certain times in the future. I was used to have a program called Fmail that I had created 30 years ago now that sent mail in the future. And it's a good question how far out the longest Fmail programs are in that Fmail specifications are that I created, I don't know, 30 years ago or something. I don't know. I haven't. It's always one of these practical things that you create a system like that, and then there's a question of how, does it keep working long enough that when it's going to send a message 20 years in the future, do you get it? Is it, how does that work? I have long wondered about the creation of a digital time safe, something where, for example, you could say, I'm going to encrypt this thing, and in 100 years, it's going to decrypt itself and tell the world about it. And I've wondered how to do that. And I have to have a think about it again, because with modern blockchain technology, there might now be a way. The last time I thought about it, there really wasn't a good way to do that. There wasn't a thing that will deterministically happen in 100 years. And I mean, one could do things where one says, when the planets line up this way, then this will happen. Kind of reminds me of the movie 2001 Space Odyssey that came out 50 something years ago, that had this idea of, the aliens leave this beacon on the moon, and its way of knowing whether there's intelligent life on Earth, so to speak, is, does it ever see the light of the sun? Because it's been buried. And if somebody excavates it and it sees the light of the sun, then something happened, there was some event that was significant. Now, of course, in reality, there might have been some meteorite impact that exposed this thing to the sun, and that would have been a false positive, a false signal for it. It's just a movie, not reality, so to speak. But there's sort of a question of, could you have something which in some kind of reminds one of the Druids and Stonehenge and all that kind of thing, when the planets line up in just such a way, then things open up, and the mysterious kind of secret chamber opens up, and the secrets of the past are revealed. It's something where people from time to time will have these time capsules where people will store them in the foundations of buildings. Recently, I guess there've been some that have been found that were stored in the foundations of statues and so on. I think that this idea of, we'll put a time capsule somewhere and people will find it a long time in the future. I know in times of the Babylonians and things like that, people would put in the foundations of temples that they built and things like this, things that said, were messages to their enemies saying, if you're seeing this, you're cursed. In other words, if you destroyed this building that had been built and you've gotten down to the foundation stone, then, just, know that, you're cursed, so to speak. And that was kind of a thing there. But in more recent times, people have kind of buried these time capsules of various kinds. I'm afraid the history, I had a little look a couple of years ago about sort of what had happened to time capsules from the past. And it's a sad story. People usually forget they buried them. And then when they open them up, what's there isn't that exciting anyway. And it's all stuff where we know the history and it wasn't something very surprising. But it's sort of an interesting question. Can you make a digital time safe where you store information that will be, for example, encrypted until some particular time in the future when it could be decrypted? I mean, in a sense, the proof of work concept of blockchain is a little bit like this idea of, you do a lot of computation to get to a point. But again, I have not been able to figure out sort of a protocol where you can have something which is encrypted until a lot of stuff has happened, and then it will automatically decrypt itself. It's let's see. Huh. The question here from Hamid: is it possible to have a civilization purely based on biological technology, for example, building microscopes, airplanes, etc., out of organic materials and by growing them somehow? You know, people used to say, I remember people saying this in the early 1980s and 1970s and so on. People who like to be contrarians saying, oh, this electronic stuff, it's just a fad. Really, in the future, everything will be grown biologically. Well, what I think is true is that biology is our one example of molecular scale computation, and there will be more. Molecular scale computation will be a thing. And right now we say, you know, we make something, it's made of plastic, it's made of metal, it's made of whatever else, it's made of some material. And then we say we can build a computer out of a material. I think in the future, we will be able to say everything is made of computers. It's, you know, down at the molecular scale, everything we're dealing with will be a programmable thing, just like the components of a computer are today. So in that sense, this idea from biology of molecular scale computation will be something that is a ubiquitous thing, true of everything out there in the world. Now, the question of, is it grown? Is it something where there is a process where not only is it programmable, but it also grows itself? It's an interesting question, whether that is a sensible way to do things. In other words, rather than making a mold to produce a particular thing or having a producing device that produces things, have the things grow themselves. It's an interesting question whether that's worthwhile, and when is it worthwhile to sort of grow yourself versus be imprinted, be stamped out, be templated in some way. I'm not sure what the answer to that is. My guess is that there will be some things that are convenient to grow, but a lot of stuff, it's easier to have an external sort of manufacturing of the thing, and then to have the thing itself be something which no longer has the apparatus to manufacture itself. I mean, if we look at biology, there's a certain amount of our capabilities which are merely, purely for the replication of cells and things like that, for the creation of new material. And if we ignored that, if we said everything is the way it is, and it's all been sort of stamped out, then perhaps we get to do certain things more efficiently. I'm not sure. I mean, biology, the idea that you will be able to make a new cell when an old cell in this particular position in space, fails or something, that's actually a pretty good idea. And the notion that you could have sort of a self-healing technological system that would grow another part of itself is not such a terrible idea. But, you know, there are things like airplanes, for example. I mean, I think back in the day, a couple of hundred years ago, when people were thinking about, you know, the expedition to the moon, they imagined, I remember when I was a kid, at least, seeing these kind of sort of early science fiction-ish books where people would, instead of having a bunch of horses pulling a horse-drawn carriage that was going along on the earth, they would have a big flock of geese or something that was hooked up to their spacecraft, and they would be being pulled to the moon by a collection of geese. Clearly not a thing that's actually going to work, but one could imagine that it would have been an interesting thing whether that had developed. Actually, I don't know. Why did that not happen? It's an interesting history of technology question. Why didn't it happen? Because people had gliders long before the Wright brothers, long before powered flight. People had gliders, and they knew if you were able to pull a glider along fast enough, its wings would get lift and it would be able to fly. And so the question is, why did people not take birds and have them and hook them up to a glider, have a whole flock of birds, you hook them up to a glider, just like you put a harness on horses, and you have that flock of birds pull your glider along and pull it fast enough that you get lift on the wings. My guess is the reason is because birds aren't powerful enough, but maybe, I wonder whether people tried that. I don't know. Maybe nobody tried it. Maybe it was, but otherwise we could have had a technology where, you know, back in the 1800s, we could have had people doing kind of the, for luxury travel, or for warfare or something, having something where you had the bird-drawn plane, so to speak, flying around. My guess is that the detailed dynamics of that don't work out. And possibly even it's the big innovation that the Wright brothers had in making powered flight in, when was it? 1905, right? Or 19, around that, first decade of the 1900s. But in any case, the thing that was one of the big innovations was being able to control the plane. It's one thing to get lift; it's another to be able to control it and not to have it sort of spiral around and sort of crash into the ground. And that innovation came when powered flight also came, and that innovation might have been needed to make a bird-drawn glider work. So maybe it's a thing even for today. But it's sort of interesting that, for example, drones of the like quadricopters and things like that, they only became practical when battery capacities reached a certain point and when computer speeds reached a certain point where you could control the thing to make it a stable flying object and so on. So the dynamics of when the bird-drawn airplane becomes possible, I don't know what the sort of breakpoints for that are, but I have to say it would be very stylish to have some kind of geese-drawn thing, and particularly maybe the geese are hard to train. I don't know. That's always an issue. One of the mysterious things with different kinds of animals and so on is some are easy to train, some are not. I know it was a very kind of premium thing to have a zebra-drawn carriage, because zebras were notoriously difficult, even though they're very similar to horses. They were notoriously difficult to train, to get them to say, yes, you really are going to walk in this direction rather than just go off and do your own thing. But in any case, okay, I think by the time we've descended into talking about geese-drawn airplanes, maybe it might be time to stop. And this question about making things out of organic materials, as I say, the organic materials tends to mean things like amino acids and so on. Whether the molecular scale computing that we will do will piggyback on the particular last 3 billion years of evolution that life on Earth has had, I'm not sure. I think it will be a little bit bizarre and perhaps even disappointing if we had to do that, because I think there are many historical artifacts in the way that that was constructed that we can probably do better than. But that's and then the question is more to the point is whether there is growable stuff or whether it is imprinted type stuff. And actually, as I think about it, there might be good arguments for having some growable type stuff that might look a lot more kind of lifelike in a sense than the things we're used to. And I would say in general that the idea that we make engineering structures that kind of look simpler than living systems, that is very much a feature of our ways of thinking about engineering, that we always want to be able to kind of foresee what the outcome of the engineering is going to be. And so we end up with these things that have a somewhat simpler structure than the possible structures that could exist in nature, or the possible structures where you could pick any one of these structures and you just select the one that happens to work. That can lead you to much more complicated looking structures where we're much less able to foresee by doing sort of pure thought or pure calculation what's going to happen in that particular system. All right, well, I think we should wrap up here. So thanks for joining me, and see you another time. And please, I think there's a mechanism for sending in questions and topics beforehand, but otherwise, please come Friday afternoon and ask whatever you want to ask. It's always interesting for me to try and respond to these things. And sometimes, well, today I know there were a number of explanations that I was able to give you, which I don't think I've ever expressed before or really untangled as explanations before. So it's really, really great to have the impetus to do that. So, well, thanks very much. See you.